Hello everybody and welcome to Chapter 9. So in Chapter 9 we are going to be focusing on what is referred to as repeated measures t-tests. Now repeated measures is not a phrase you're going to see everywhere in stats, and in fact I think most textbooks refer to this as paired samples. So if you're going to be looking up anything on this chapter online, if you want to look up other examples or anything like that, you might want to use the phrase paired samples t-tests. Because that's more commonly used, as you'll see in JASP, actually. Alright, so this chapter, what are we going to be doing? We're going to be talking about what the paired sample t-test is, how we calculate it, when we would use it. This format for this chapter is going to be very similar to previous chapters, where we're basically going to walk through kind of the conceptual aspects of it, and then drill down in the 4 steps: the hypothesis, the t critical value, the t obtained value, and the make a decision phase. We'll also talk about how to calculate the effect size and the confidence intervals. So let's get into it. Alright, so both the z-test and the t-test that we have been looking at so far generally focus on one sample. In other words, you get one sample, you have so many people in it, and then you analyze that and you compare that against some other ideal. Sometimes that's a population, sometimes it's a test value. In the case of a t-test, if you're doing a one sample t-test and you're trying to test against 100 or test against 0, for example, in either case you're using one sample to do that. Now, that's not the only kind of data you're going to be collecting, right? Or the only kind of data you're going to be interested in as a psychologist. A lot of times, one of the things that we are interested in as psychologists are change over time. So in other words, how does someone's behavior change over months, over years, over weeks? That is something that we can systematically test and that we can study, and it's super important for us as psychologists because, especially those of you that want to be therapists or clinicians, that's kind of what you want to see, right? Is you want to look at change over time. How much has your patient changed over time? Is your treatment working or not? These are the kinds of questions we can answer using this new kind of t-test. So there are 2 types of t-tests for us to be able to measure more than one sample, and those are the independent samples t-test, which we'll be talking about next chapter, or the paired samples t-test. As I mentioned, the book refers to this as repeated measures. I'm going to be calling it paired samples because outside of this textbook I haven't really heard many people use repeated measures. Alright, now the key phrase for this chapter that encapsulates everything you need to know about this t-test, this paired samples t-test, is this one word: change. Because what we're looking at is whether one sample changes over time or changes between conditions, and we're going to build a hypothesis out of that. So does your sample change? Here is an example here. Let's say, as I mentioned, you came up with an example that was measuring change over time as a therapist. So you are going to give these people a quantitative stress inventory to all of your clients on your first day. The QSI is going to be essentially it's kind of, people think of it kind of like, not exactly a measurement of anxiety, but pretty close to that. Also kind of a measurement of life satisfaction. In some cases, some people have used it to look at that. So basically we want to look at whether or not this value for how people do on the quantitative stress inventory, whether or not that changes before and after you administer treatment to them. In this case, I have it where you give it to them before they begin treatment and then 1 month after treatment. So you can see for the QSI that those scores change from 122 to 111. This one person went from 131 to 116. This one person went from 127 to 113. This one person went from 123 to 119. And this one person went from 132 to 121. Now, if I were to ask you, does it look like people's scores are changing? Every single person would probably say yes, right? But again, just like in the previous tests, we can't just eyeball it. We have to, and we can't just subtract them and see if it's a positive difference or a negative difference. We have to run stats on it because running statistical tests is going to tell us essentially whether or not we have a meaningful change once we account for variability and variance. That's going to be key issue for you as a therapist. You're going to see all kinds of different people who are all, their behavior are all changing at different rates. and frequencies. And so you need to be able to account for that variability. So that's why we are using statistical testing to do that. And I should mention that the larger the score here represents the more stress, the lower the score represents less stress. So how do we properly compare them? In some cases, it's going to be kind of weird because it's not super intuitive. That's why I try to emphasize the word change, because we're not actually really going to be comparing this sample over to this sample. Instead, what we're going to do is we are going to look at the change between each of these values and then run a test on that change. So this is, you can think of it as like kind of comparing two samples like this, or you can think of it as running stats on the change between those two samples, which is a slightly different connotation, but you'll see how it's different in just a moment. Now, crucially, we don't have a population here. We don't have any kind of population we can compare against. Instead, we're just going to be comparing against this piece right here, the before section. We're going to consider that as kind of like a baseline to look at whether or not there is change over time. All right, so and when we say the word change, we can also refer to this word difference. What is the difference between these two samples? So conceptually, what we're going to be doing is we are actually going to kind of run a one sample t-test on the differences between your before and after score. I'm not going to repeat that all that much because I don't want you to internalize that lesson, but I'm just trying to emphasize that a lot of the tools that you're going to see are very similar to what you've been looking at previously this semester. There are going to be some familiar faces in the formulas that we use, but they look a little bit different, and you have to be careful because when you're calculating it, when you're doing it by hand for a quiz or for exam, your approach is going to be very different in the beginning, and then you'll see very quickly it becomes the same old thing you've been doing the past couple of chapters. Alright, so in a paired sample t-test, what we're doing is we're comparing one sample against the other and looking for that difference and then understanding that difference. So if these two samples appear to be statistically different, then we can say that they come from two separate populations. Why is that important? Because if I'm saying that before and after are fundamentally different, then we can treat them then as if they come from two separate populations. In other words, a hypothetical population of people before your treatment and then a hypothetical population for those outside of your treatment. In other words, you can't mix those two groups because they are fundamentally different, which is important. That's what you want to show as an effective therapist. So the before population is going to be participants before they experience therapy, and the after population would be all people who had some experience with that particular therapy. If they are not different, so if we run this and we fail to reject the null, then the way that we would phrase that is essentially that we would assume that those two samples come from the same population if you fail to reject the null. If you do reject the null, then what you're saying is that these two samples cannot come from the same population. There was a meaningful statistical change over time. Here is one key part of our formula. Difference equals time 2 minus time 1. So we're going to express this in xd. So xd is going to be equal to the x of time 2 subtracted by the x of time 1. And ultimately we're just looking at whether or not there is a difference between these samples, and we're going to test them. So, sorry, I'm fast forwarding through this because I want to show you some of the math, because I feel like it'll be a little bit clearer then. There's going to be two ways that we can express this hypothesis when we're talking about paired sample t-tests. They essentially mean the same thing, but you can phrase it like this. This is for the null hypothesis. So you can phrase it like the null hypothesis is that population 1 is equal to population 2. That's fair. But what that would mean is that the population difference between those two is equal to 0. So in other words, a null hypothesis would say that the difference between sample 1 and sample 2 is 0. That's one way to talk about it. So if we think about what that would look like as an alternative hypothesis, we could stick with the old school format, which we've been doing. With the alternative hypothesis is going to be equal to mu1 is different than or greater than or less than mu2. But if we wanted to use this new notation of the mean difference, you can see how this is a little bit idiosyncratic. where we have the alternative hypothesis where the mean difference not equal to 0. And so what does that mean? If the mean difference is not equal to 0, what that means is that you are suspecting that there is some difference between your two samples, but you're not sure which one is going to be bigger than the other, or faster than the other, or whatever. You don't know if time 1 is going to be larger than time 2, or if time 1 is smaller than time 2. So it's two-tailed for that way, because essentially you're drawing out your distribution and you're saying we could find people over here, or we could find people on the other end of this distribution. So if we decided to phrase it like this, where mu d is greater than 0 and mu d is less than 0, then what that means is that for mu d is greater than 0, that you had significant increase in scores between time 1 and time 2. Means that maybe your performance got better as a function of time. For this one, mu d is less than 0, then we're saying that scores decrease from time 1 to time 2. Now, did I see in our test over here, so I'm going back to our example. Okay, I didn't specify if there was, which direction there was, if I should do a one-tailed or a two-tailed here. I'm just making sure I don't see that yet. All right, so that's going to be the first part here. Now, if I said that I suspect that with my treatment that scores have gotten better, that means that scores have decreased, and so we would say that this one right here, that the alternative hypothesis is the best one to go with, that mu d is less than 0. In other words, we are expecting a negative change over time. All right, so the critical values, we're going to find these exactly the same as we found the other ones from the previous chapter. We're going to refer to our t-critical calculator. And we need to know the same amount of information. We need to know the alpha value, and we need to know the degrees of freedom, and we need to know if it's a one-tailed test or a two-tailed test. For the sake of this example, we're going to use a two-tailed test. We're going to look to see whether or not there was any difference between our time 1 sample and our time 2 sample. We haven't made a prediction about whether they have gotten better or worse, though. So here, again, we're using degrees of freedom of n minus 1. So just like last chapter, we are going to be using this value where we're going to be plugging in the total number of participants and then subtracting from that 1. Now, don't get too comfortable here, because next chapter we're going to be calculating degrees of freedom as n minus 2. But we'll talk about that once we get to it. Alright, so if we were to plug in those values, I can show you what that looks like. So the degrees of freedom here, how many people did we have in our, sorry, let me just backtrack for a second. How many people do we have here? 1, 2, 3, 4, 5. We had 5, which means that we are going to be looking for, a degrees of freedom of 4 and an alpha value of 0.05. I hit calculate, and you can see here the two-tailed test is going to be positive negative 2.78 once we round up for that. So what does that mean? Basically, if I come back over here and I draw this out, and I have a graphic in a couple of slides that will probably illustrate this better. But basically this means that we are going to be setting up these critical thresholds, negative 2.78 over here and positive 2.78 over here. So when we get our t obtained, if it falls below negative 2.78 or above positive 2.78, then we can reject the null hypothesis. Alright, so this is exactly what you were just looking at. The reason why this is a very extreme value is because we're using an alpha value of 0.05, then we're using 5%. We're saying that there's 5% chance that the results we got were due to chance and random variability. So 2.5, we're going to be taking the 5%, we're going to split it in half so that 2.5 is in the bottom half and 2.5 is going to be in the top half. Or maybe I should say the top extreme and the low extreme. Alright, so here is how we calculate the test statistic. Again, it's going to be very similar to what you've done before, but there is a key crucial step that is easy to miss, so be careful here. Last chapter, this is what we used. We used this, where we have the sample mean subtracted by the population mean divided by the sampling error. Because remember, the sampling error is going to be the standard deviation divided by the square root of n. Okay, the paired sample t-test score, as you see, is very similar. But what's the difference? Well, the biggest difference is that it has D right here, right? Like what the heck is up with this capital D? Remember, that's looking at the difference. So what we are saying here is we are looking at our sample's difference between time point 1 and time point 2. We're going to subtract from that what we think the difference might be based on our null hypothesis. So I should specify up here that this is the null hypothesis' mean value here. And we're going to be dividing that over the sampling error, which, as you just see up there, is going to be standard deviation divided by the square root of n. Alright, so in most cases, this mu d is just going to be a big fat 0. It's just going to be 0 because your null hypothesis is predicting there to be no difference between your samples, which means that it would be a difference of 0. Now, the ingredients that we need here is going to be the mean difference, the hypothesized difference, and the standard error of the difference values. So for all of this, like I mentioned at the very beginning of the chapter, it's maybe less that we are testing two samples and more that we are testing the difference between those two samples. So here's how this is different. This is the biggest, most complicated part of this chapter. That whenever you are calculating the standard deviation for this data set is not going to be going the way that you think that it is. So remember, we have 5 participants. We do not have 10 participants. This is a sample of 5 that we're going to be getting twice. So we have their before scores and their after scores. What we are going to do is we are going to subtract each of those so that we're left with the difference. So in this case, I have negative 11 because, and I should say that this is, whenever I get this is time 2 minus time 1. And that just lets us know whether or not there was a decrease or an increase in our data. So this is negative 11, which means that it decreased between time 1 and time 2. 131 to 116, we know that's a decrease. It's negative 15, and so on. So we see that we have our different scores here. And now we can do the exact same thing we've been doing all semester with standard deviation. So we can effectively, if I had written all this out, I could very dramatically say like, all right, we no longer need the before and after. Like all that stuff we no longer need because what we're really interested in here is the difference in the change over time, and that's what we have right here. So now that we have these values, these are going to function like your X column whenever you're normally calculating a sample standard deviation. You're going to be taking these values and you're going to be subtracting from it the mean. So the first thing that we need to do here is to calculate the mean. The mean difference is going to be about 11 points, which means I'm going to be subtracting each of these by 11. So 11 subtracted by negative 11 is going to be 0. Negative 15 subtracted by negative 14, which is essentially like adding 11, is going to be negative 14. Negative 14 subtracted by negative 11 is going to be essentially negative 14 plus positive 11 now. That's going to give us negative 3, so on and so forth. So you get the idea. And I can even add these up. This is negative 7. And if I add that to positive 7, it gives me 0 for this column. So I know I'm on the right track. I just did the math to double check that. Now we're going to be squaring each of these. So we're going to be squaring each of these numbers because we cannot add them all up together. And when we do, that is your column. When you add them up, it should give you 74, which means that you have a sigma d, a sigma xd is going to be equal to 74. So you crunch the numbers and you came up with 74 as your sum of squares. You're probably feeling pretty good about yourself because now you just figured out this part of the equation, which is the hardest part of the equation to figure out. So I'm going to plug in 74, my sum of squares here. I'm just adding that there because I know it can be easy to lose track of what that value is supposed to be. And we're going to take that 74, we're going to subtract that by the degree, the sample size minus 1, which is effectively our degrees of freedom. And so when we crunch that, that should give us the square root of 18.5, and when we simplify that, it means that our sampling error is going to be 4.301. And actually, I take that back, is that this is the standard deviation. So the standard deviation is 4.301, which means we need to take 4.301 and we need to divide it by the square root of n. So when we do that, that's what you see exactly over here. We can square root of the sample size, and that gives us about 1.92. So what does that mean? Basically, it means that our difference here between our different scores is roughly about 2 points away from each other at any given time. So if I'm to try to calculate this, I'm going to just plug in these numbers now. So this is going to be x bar d. This is going to be mu. Ooh, that looks bad. Sorry. That's going to be mu d. And then over here we have the standard deviation, or sorry, the sampling error difference. And that gives me a t equals negative 5.72. Now we have to make a decision. And you may have already drawn something like this, but if I'm looking here and I see that I need a negative 5.72, that is going to be way over here, right? Which, not always, but usually is a warning sign. If your stats are that significant, usually means that there might be something weird going on. But in this case, it's fine. So we are going to reject the null hypothesis because we exceeded that critical t value. So we would write this in APA format by saying something like, based on our group of 5 clients, therapy reduced stress scores, and then I would put the mean difference in that stress score, which is negative 11, after 1 month of treatment, and then we specify the test that we used. It was a t-test, the degrees of freedom. Sorry, let me write out some of these. The t obtained, and then the alpha value. And last but not least, the p is referring to the p-value. Alright, so yeah, our t-score is way out below that threshold. It means we need to reject it all. Alright, so confidence intervals, as I mentioned in the last chapter, are another way of testing hypotheses, and to get a good idea of what your data should look like, you can run one of these. So if we're using a one-sample t-test, this is what the confidence interval looks like, which, so you may remember it. We have over here, this is the margin of error, right? So this is the t-critical multiplied by the sampling error. Sorry, my dog is barking. Sorry, my dog was barking at nothing in particular. He is so passionate about confidence intervals. Anytime I get started, he interrupts me. But you may remember that this part of the one sample t-test is referred to as the margin of error. And we're basically going to do the exact same thing here again. But again, the difference here is that we are not going to be looking simply at the mean values for this or the regular standard deviation. We're going to be looking for the mean difference and compare that, and then also factor in the standard or the sampling error difference as well. So when we look back at our formula here, when we're like trying to solve confidence intervals, we're going to be using this mean difference and this standard deviation difference. So that's where those numbers are going to come from. So the mean should be the mean difference, for example. So here is our ingredients from the last example, where we have the mean difference is going to be equal to negative 11. The standard deviation is going to be equal to, actually, hold on, let me make sure that's the standard deviation. Okay, yeah, just making sure. I wasn't sure if I accidentally put the sampling error, but we got our standard deviation here. We have the total number of samples here, our sample size, and we have the alpha value. But we can use these ingredients now to calculate our confidence interval. Now this is going to be a 95% confidence interval because the alpha value is 0.05. We're going to look at another example with what happens whenever you change that number. So here we go. This is a 95% confidence interval, so we can be 95% confident that the actual population difference between sample 1 and sample 2 is 0. Alright. So, we're going to plug in these numbers. So the t-critical was 2.78, the standard deviation was 4.301, and then the square root of 5, we're going to be dividing all that by that. And then we are going to be adding that to our mean difference. And our mean difference here was negative 11. And so when I plug in those numbers, this gives me the denominator that we saw when we were obtaining our test statistic. So you may not have to do these whole steps all over again. If you remember, what the sampling error was. And you're going to be multiplying that by your t-critical, and then adding that value. In this case, it's 5.34. We're going to be adding that to the top of negative 11, and we're going to be subtracting it from the bottom, which gives us negative 16.34 and negative 5.66. So how do we interpret that? And we would actually write this out usually as something kind of like this, where you have it in brackets like that, and then the low number is always on the left, the high number is always on the right. How we would say this is that we are 95% confident that our sample comes from a population whose mean is between these things. And I should say that our sample difference comes from a population change between whose mean is between this. And I guess population change also suggests that we're looking at differences here. I just felt like I needed to stress that. So if we wanted to look at a 99% confidence interval, then we can also try that. And actually, sorry, let me back up one more time. The way that you can use this confidence interval to test whether or not you need to reject the null is by looking to see whether or not your hypothesized difference according to the null is within this interval. And because you may remember me mentioning, that's almost always going to be 0 is what you're testing against. Almost always. For our class, I think pretty much always it's going to be 0. So here, does 0 fall between these values? It does not, which means that we're 95% confident that our population difference mean comes from somewhere between these two estimates, but it's highly unlikely that it is 0 at this point. So if we plug in the same values for the 99%, really the only thing that changes is going to be the t-critical value. That's the only thing that changes, as you can see here, as these values stay the same and as the mean difference stays the same. So now we are adding and subtracting 8.86 to a negative 11. And even then, we can still reject the null. How do I know? Because 0 does not fall between these specific parameters. So we can reject the null. We can say that we are now 99% confident that our sample comes from a population change whose mean is between those values. And then finally, I feel like I've rushed through this, but I think it's just because there's so much overlap between previous chapters. You know, like you already know how to calculate a t-score at this point. At this point, it's just kind of practice. Because I was going to say, if you feel like I rushed too much, just email me, let me know, and I'd be super happy to talk with you and answer any questions you have about this stuff. The last thing that I want to talk about how to calculate is the effect size. So the effect size, if you remember, the effect size is all about how much of a difference does your condition or does your treatment or does your curriculum make on the data. So the larger the value here for our effect size, the bigger a difference the introduction of that treatment makes on your clients. That's one way to think about that. So it is possible to have a statistically significant t-score, but a very, very, very low d-score. That's totally fine if you have that. And in fact, if you work with big, broad populations that are non-clinical, in other words, that they are not, you know, like they're just like regular college students or whatever, usually you're going to have some pretty small effect sizes, but they can be statistically significant because it holds on to a very consistent pattern. So we're going to be doing this probably the way that you imagined, where we are going to be subtracting, instead of calculating Cohen's d by subtracting the sample mean by the population mean, we're going to be subtracting the sample difference by the hypothesized difference, which again is almost always 0. And we are not going to be dividing that by the sampling error, we're only going to be dividing that by the standard deviation. So for our first example, this is what it looks like. We have negative 11 subtracted by 0, so it's negative 11 divided by 4.30, and this effect size is off the charts. This is a huge effect size. You'd be lucky if you get anything over 1, but to have it here, that's very impressive indeed. So we would say that not only is this a statistically significant effect, it's also a very meaningful effect. That it clearly has big changes on their data whenever they go through treatment. Now, the last thing that I want to mention here are order effects. This is something that you've probably talked about in research methods, but I wanted to bring it up here because just because you find a difference between time point 1 and time point 2 does not always mean that your conditions work, or that your whatever you did between time point 1 and time point 2 was helpful or effective. Instead, it may also be what's called order effects. And order effects is just the idea that the order in which you go can mess with the results of your data. So, you know, one example would be like, let's say that you were interested in looking at the effect of looking at pets. Well, I was about to use a student's actual project, but I feel like that might be too weird. They might not be okay with that. So let me give you another example. Let's say that I'm looking for the effects of mood on how much I enjoy TV. And so the way this experiment works is that if I'm in a bad mood, they're going to show me an episode, and then they put me in a good mood and make me watch another episode. So what happens if there is no difference between those? Is it because we don't have any difference if we watch mad versus while we're happy? Maybe. But it also could be the order effects, where just by watching that really, or being in a melancholy mood at the very beginning may, in turn affect how we feel later down the line. And if we did it in reverse, where we did the good mood first and the bad mood second, maybe that trend goes away. If it does, then we are saying that order effects are going to be responsible for this data. So the way that we prevent this is with a method called counterbalancing. And this would be like if you have multiple time points, that you try your best to arrange them into different things. Or if you have a different condition, you might try to give people different conditions at different times. So, like the example that I gave about being in a good mood or a bad mood and watching TV, you want to not just keep it that same sequence all year long. You want to try to split it up so you have half of all people doing one condition first, then the second one, and then have the other half do the second one first and then the first one second. That's just something to be cautious about. It's probably not going to come up too much in our math, but it may come up in a little bit of the theory quiz. But other than that, that's pretty much it. Thank you so much for your time and attention. I'm going to make one quick video showing how to kind of walk through each of these steps using a brand new example from scratch. So if you're interested in another example of this, how about you come on over to the next video and we can learn that together. I will see you later. Bye-bye.